Series 1, Discovering Time, Episode 18, The Eclipse That Changed Physics. By 1905, Albert Einstein had achieved something extraordinary. His special theory of relativity had shown that time was not universal, that moving clocks ran more slowly, and that observers traveling at different speeds could disagree about the timing of events. Yet Einstein himself knew that his work was incomplete. Special relativity only applied to observers moving at constant speeds. It said nothing about gravity, and gravity remained one of the deepest mysteries in science. Newton had described gravity as an invisible force acting instantly across vast distances. It kept the moon in orbit around the Earth and the planets circling the sun. Newton's equations worked remarkably well, but even Newton admitted that he did not understand how gravity itself operated. The idea that one object could somehow pull on another object across empty space troubled Einstein as much as it had troubled Newton 2 centuries earlier. Then, in 1907, Einstein had what he later described as the happiest thought of his life. He imagined a man falling from the roof of a house. As the man falls, he drops his keys, his wallet, and anything else he happens to be carrying. To the falling man, those objects appear to float beside him. For those brief moments, he experiences no sensation of weight. He feels exactly as though he were drifting through empty space far from any stars or planets. Einstein then imagined another scene. A man is sealed inside a lift floating in deep space. The lift has no windows, so he cannot see outside. Suddenly, rockets attached to the lift begin accelerating upwards. The man feels himself pressed against the floor. If he drops a ball, it falls to his feet. If he jumps, he lands back on the floor. To him, it feels exactly as though he were standing on the Earth. Einstein realized something astonishing. There was no experiment that the man inside the lift could perform to tell whether he was standing in a gravitational field or simply accelerating through empty space. Gravity and acceleration seemed to be two different descriptions of the same phenomenon. This idea became known as the equivalence principle, and Einstein suspected it was the key to understanding gravity. At first, he thought the problem might be solved quickly. It was not. For the next 8 years, Einstein struggled. He repeatedly believed he had found the answer, only to discover mistakes months later. He sought help from his university friend Marcel Grossmann, who introduced him to a branch of mathematics developed decades earlier by Bernhard Riemann. Riemann had studied curved surfaces and curved spaces. To understand his ideas, imagine an ant walking across a giant beach ball. The ant believes it is traveling in a perfectly straight line, yet someone watching from outside can clearly see that the path curves because the surface itself is curved. Einstein slowly realized that perhaps gravity was not really a force pulling on objects at all. Perhaps the presence of matter curved space and time themselves, and planets merely followed the straightest paths they could through this distorted geometry. It was an extraordinary leap of imagination. For centuries, people had thought of space as an empty stage upon which events unfolded, and time as a universal clock ticking away in the background. Einstein was proposing something completely different. Space and time were not passive spectators. They could bend, stretch, and warp. In November 1915, after years of frustration, Einstein finally completed his General Theory of Relativity. Almost immediately, it solved a mystery that had puzzled astronomers for decades. Mercury's orbit behaved oddly. Its closest approach to the sun slowly rotated over time, and Newton's theory could not account for all of the movement. Einstein's equations predicted exactly the missing amount. But Einstein wanted a more dramatic test. He realized that if gravity curved space and time, then even light should be affected. This sounded absurd to many physicists. Light has no mass. How could gravity pull on something with no weight? Einstein's answer was subtle. Gravity was not pulling on light. Instead, light simply traveled along the straightest possible path through curved spacetime. If spacetime itself was distorted by the sun, then starlight passing close to the sun would appear to bend. Normally, this effect could never be observed because the sun's glare hides nearby stars. But during a total eclipse, the moon blocks the sun's light and allows astronomers to photograph stars close to its edge. Einstein calculated that these stars should appear slightly displaced from their normal positions, not because the stars themselves had moved, but because their light had traveled through curved spacetime surrounding the sun. Then, history intervened. The First World War broke out. Scientific collaboration between nations almost ceased. Einstein was German. Britain and Germany had been enemies. Yet one British astronomer believed that science should rise above politics. His name was Arthur Eddington. Eddington organized expeditions to observe a total solar eclipse in May 1919. One team traveled to Sobral in Brazil, while Eddington himself journeyed to the island of Principe off the west coast of Africa. Clouds threatened to ruin the observations. For much of the eclipse, the sky remained overcast. Yet, just at the crucial moment, gaps appeared and photographs were taken. Months later, astronomers compared the eclipse plates with photographs of the same stars taken at another time of year. The stars appeared slightly shifted, exactly as Einstein had predicted. On the 6th of November 1919, the results were announced in London. Newspapers around the world exploded with excitement. Revolution in science. Newtonian ideas overthrown. Lights all askew in the heavens. Almost overnight, Albert Einstein became the most famous scientist on Earth. The eclipse of 1919 did much more than confirm a theory. It changed our picture of the universe forever. Space was no longer an empty stage, nor was time an invisible river flowing uniformly from past to future. Together they formed a dynamic fabric called spacetime, capable of bending under the influence of matter and energy, guiding the paths of planets, stars, and even beams of light. And if gravity can bend light and distort space, then perhaps it can also affect the passage of time itself. In the next episode, we shall discover that two perfectly identical clocks, placed at different heights above the Earth, do not keep the same time, and that Einstein's strangest prediction of all turns out to be true. Thank you for watching and listening. If you've enjoyed traveling through time with me, please like and subscribe. And if the next episode is available, click on it now and let's continue the journey together.